This is a simple introduction to elliptic curve cryptography. Elliptic curve cryptography, often abbreviated ECC, is a type of public key crypto system that uses the math of something called an elliptic curve to create public and private keys. So, when we do public key cryptography, we need a way to generate a public key in such a way that it's computationally hard to compute the private key from the public key, but it's easy to compute the public key from the private key. There are one of two problems that are typically used for this in public key cryptography. The first is factoring large composite integers into primes, p, and q. The RSA crypto system is based on the hardness of this problem. In elliptic curve cryptography, we use something called the discrete log problem. The problem is finding little x such that big X equals little x times big P. Given only big X and big P drawn from G, a set of points that satisfy some special properties we'll get into next, it should be infeasible to find little x. So what is this G thing? G is a group, and all a group is a set of elements. In our case, they're going to be points on an elliptic curve, as well as a mathematical operation called the group law. The group law applies to 2 points and produces a third. This set of points and the group law need to satisfy some simple properties called the group axioms. Given A, B, and C from the group axioms are as follows. Closure. If I take any two elements in the group, A and B, and I apply the group operation to them, I should always get another element C also in the group. Associativity. It doesn't matter how the numbers are grouped when I operate on 3 or more elements A, B, and C. Changing the grouping, which numbers you do the group law on first, doesn't change the result. Identity. There's a special element that when I apply the group law to it and another element of the group, I always get back the element of the group A as the result. And we indicate the identity element using, for elliptic curves, this curly O. So for groups where multiplication is the group law, the identity element would be 1, for example. So 2 times 1 is 2. And finally, inverses. There needs to exist an inverse for every group element. So for every element A in the group, there needs to exist another element, A inverse, that when the group law is applied produces the identity element. So why is any of this relevant? So we are going to define a group over the points on an elliptic curve such that the discrete log problem is hard in that group. So what is an elliptic curve? So an elliptic curve is defined by an equation like this, y squared equals x cubed plus ax plus b. The set of points that are the solution to this equation are points on the elliptic curve. So here we're defining the curve in continuous space over all the real numbers. So A, B, our coefficients, and our coordinates x and y are going to be real numbers. So for cryptography, we actually define the curve over something called a finite field, where the size of the coordinates is bounded. So each coordinate ends up being an integer modulo, for example, a large prime number, and we'll talk more about that in a future video. But for explaining the group law, we're going to use this geometric picture over the reals. So we have our points along our curve. We also have an element in the group that's not shown here, which is the identity element, our curly O, and we call that the point at infinity. And I was unable to fit infinity on this plot, so it's not shown. So we've got the elements of our group. What about the group law? So the group law in elliptic curve crypto is point addition. So this group law is defined geometrically. So let's take a look at that. So imagine 2 points on the curve A and B that we want to add together. When you draw a line through those 2 points, it's going to intersect at a third point, the elliptic curve. And when we reflect that point of intersection across the x-axis, we get the result of our point addition. So A plus B equals C as shown here. Elliptic curves are all symmetric about the x-axis. So we've got our group law defined over our elliptic curve. So how are we going to use this for cryptography? So something to realize is when we perform point addition several times to a given point, so say we're going to add A to itself repeatedly, we're actually doing something called scalar multiplication. So scalar Scalar multiplication involves taking a point on the curve and adding to it to itself multiple times. So again, we're really, for cryptography, doing this in a finite field, the integers modulo a large prime. And it's easy to do scalar multiplication, but it's very hard to undo. So it makes it perfect for generating cryptographic keys. So if we do point addition, k times, starting at a point g, so we add g to itself, k times, we end up with a point p. And the way we write that down is this. So p equals k times g. So here we have k, our scalar, that is our private key. That's the number of times that we've done the group operation. And the public key is going to be the resultant point, also on the curve, big P. So the discrete log problem in this context is determine k, given g and p, such that p equals k times g. P, public key, k, private key. When we do this in practice, we pre-agree on what point we're going to start at, g, called the base point, and we're also going to agree on the curve that we're going to use and the finite field that is used. So you might wonder why even do this. The main advantage of elliptic curve cryptography is that it offers the same level of security as RSA with much smaller keys. So for example, a 256-bit key in ECC is roughly as secure as a 3072-bit key in RSA. So that's going to mean faster computations, lower power consumption, and less storage space. So, in summary, we've seen that elliptic curves form the foundation of most modern public key crypto systems. We've seen how we can form an elliptic curve group from points on the curve. We've also introduced the group law. And we've seen how scalar multiplication is used to generate public keys given a private scalar. So I hope this has been a helpful introduction. Please comment about other topics in cryptography you'd like to have explained.